Welcome, Travis.
Hi, everybody. All righty, let's go and share a screen and then we'll get cracking. So is that working for everyone?
I can see it.
All right, that's what we need to do. So like Sarah said, I'm Travis Kowalski. I am the head of the Department of Mathematics here. And I came to mathematics by kind of a circuitous route. I started out as an art major. And so a lot of the parts of mathematics that I tend to really enjoy have more to do with art and history and the humanities aspect of it. And so that's kind of what I want to talk about today in sort of honor of Pi Day. And so I got to fix this first off. Make sure I have things running here. This isn't, can I get the thing to work? There we go. We want to cross that thing out. This is Pietry in motion. So we're going to be talking about perimeters, poems, and pi. And so we'll open up with one of my favorite poems. There's Edgar Allan over there on the side. Midnight so dreary, tired and weary, silently pondering volumes, extolling all of my now obsolete lore. During my rather long nap, the weirdest tap, an ominous vibrating sound disturbing my chamber's anti-door. This, I whispered quietly, I ignore. Perfectly the intellect remembers the ghostly fires, the glittering ember, inflamed by lightning's outbursts, windows cast numbers across the floor. Sorrowful as one mistreated, unhappy thoughts I heeded, that inimitable lesson in elegance, Lenore, is the lightning, exciting, nevermore. So for our talk for poetry, we'll start off with one of the most famous poems that's known. So let's get the other pleasantries descended with. Happy belated Pi Day. We're going to be talking about the number pi in honor of March 14th. And we're going to talk about its connections with poetry and the fascinating and unexpected interplay between the two. So as you know, pi is this famous mathematical constant. It's given by a very long decimal expansion, 3.14159263553589799. And you're saying, hold up. One, are we not even going to talk about St. Patrick's Day at all on St. Patrick's Day? And the answer to that is no, we're not. Question number two, are you not even going to address the fact that the poem was wrong? So that intro poem that I gave everybody was not actually The Raven. That has one of the most famous openings in history. Once upon a midnight dreary while I pondered weak and weary over a quaint and curious volume of forgotten lore. What I gave you was not quite The Raven, and it even said so in the title. It was close to being The Raven. And so this weird fan fiction-y remix is going to play a role a little bit later on in our story. And so with that there, let's go and say what we're going to do here. We're going to give a talk about pi and poetry in three parts. The first part will be about the poetry of pi, the art inspired by pi and its digits. The second part will be the math of pi. It's a math talk, so we're going to talk a little bit about the history of pi and its digits. And then we're going to close with Pietry. We're going to close the circle and talk about poetry that teaches folks about pi and its digits. And so without further ado, let's go and talk about the poetry of pi. So the number pi is famously ubiquitous. It's one of the few numbers that people sort of know by name. It's this irrational transcendental number that can be approximated by 3.14. And that irrational transcendental part actually means that its decimal approximation never terminates, never repeats, and can never be expressed as a finite sum of other kinds of decimals that repeat or terminate. So it's this number whose decimal expansion just always dances off to infinity in new and exciting ways. And so that kind of tends to excite the minds of folks. But more than just being a weird numeric expansion, the number plays an essential role in a number of mathematical disciplines like geometry, probability and statistics, and complex analysis, to name a few. The picture up here is the Riemann zeta function, one of the objects that I study in abstract mathematics. But I don't want to talk about any of those things. This isn't a talk about abstract mathematics. This is a talk about poetry and art. And the thing that pi is most intimately connected with are circles. So wherever there's a circle, there's pi. Pi is hidden in the very fabric of being a circle. And that explains its ubiquity, why pi pops up in so many cultures, why it plays a role in art and mathematics, because we're just surrounded by circles. We live on a giant circle, which we subdivide by vertical circles and horizontal circles. In the sky during the day, we get light by a giant circle. At night, we get light by a giant circle. If we have something fixed on a pole and we tether, say, a goat to a pole, it eats in a circle. We have irrigation circles. They are both divine and mundane shapes to us. And so these shapes become metaphors for things. Circles pop up as sacred geometries and common metaphors. They express symmetry. They express balance. They express periodicity, the facts that certain things cycle over and over and over again. Wherever you've got circles, you've got metaphor. Wherever you've got metaphor, you've got art. And so pie and art are sort of inexplicably connected. Just to kind of show you this right here, these are two pictures that have nothing to do with art. These were images that I generated for a completely different, utterly mathematical talk on stars built with straight lines and stars built with circular arcs. And even if you knew nothing about the math that went behind these two things, these are just sort of beautiful pictures. It's very hard for these things to not be connected to each other. Math and art have this long history. At a technical level, mathematics, things like geometry or number theory, they're needed for the creation of art. Geometry is needed for knowledge of perspective, to use it properly or to break it. It's needed for understanding the chemistry of mixing colors. Number theory is needed for the creation of music and tones that work together. But more fundamental than this technical idea, mathematics and art are the means by which humans seek to understand and give meaning to the world around them. Mathematics is a way of doing it at a quantitative level, and art does it at a qualitative level, but they're two very human languages for talking about the world around them. Just as a very interesting example, there's a long tradition of mathematics being written as poetry. The Vedic Hindu tradition, these are mathematicians from India, they would express their mathematical truths as poems in Sanskrit. One of the most famous of these mathematical treatises is called the Lilavanti, which means the beautiful or the beloved. And it's a textbook on number theory and geometry. And it looks like what you see up here, this sort of beautiful Sanskrit penmanship, but it's clearly a math text. You can see things like triangles and shapes. This is a page on geometry. This is a page on number theory. I'll actually get to one of the poems a little bit later when we actually talk about poetry in specific. I do want to point out that this particular poem is famous because it's one of the earliest instances of the symbols that we now use as our numbers. What we call the Arabic numbers are actually the Hindu Arabic numbers. And you can kind of see a 1, 2, 3, 4, 6, and a 9 in that's the pattern that I've circled right there. So clearly, beautiful art involving circles is going to involve pi in some sort of fundamental way, since pi is inexplicably tied to circles. But it's kind of a stretch to say that the number pi itself, the 3.14159, is what inspired the artwork. And that's kind of what I actually want to spend a lot of my time talking about, is art that's inspired not by the concept of pi, but by the actual number pi. Pi Day is a celebration of the decimal approximation 3.14. Is there art that celebrates the decimal approximation of pi? If you sort of think about it, if you're going to somehow have to work the digits of a number into your artwork, that's going to sort of put constraints on it. There are visual ways to work around these constraints. Here are two pieces of art, one by Christian Basale, who is a mathematical artist. And one of these is a crop circle that appeared outside of the Banbury Castle in England in 2008. And these are both geometric representations of the number pi. His artwork is an actual tracing of pi. If you start at the very top of the little mark that says 3 and follow that little filament bit by bit, it starts from 3 and goes to 1, then goes from 1 to 4, from 4 back to 1, from 1 to 5, from 5 to 9. And as you follow these filaments through, it traces out pi to 1,000 decimal places, starting with the 31415.9. On the right, there is this crop circle. The crop circle is actually a really clever way of representing pi. I'm going to put in some helper lines in it just so we can kind of understand a little bit better. If you go and divide the circle up into even tenths, starting from the inner circle and reading clockwise, each of the arcs will pass through a certain number of these, and the number of sectors that they pass through is the decimals. So the first arc starting from the center sweeps through 3 of these, 3. Then there's actually a little decimal point carved into there. 1, a sweep of 4, a sweep of 1, 3.14, 1, 5, 9. Every circular arc counting another digit of pi. This goes out to, I believe, 15 decimals, and it ends with the 3 ellipses right here, the dot, 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 and how we would write our own numbers. But this was a talk called Poetry and Pi, Pietry. And so let me change my perspective and not talk about visual art, but written art. The digits of pi find their way into poetry and prose, most commonly in the form of constrained writing. So constrained writing is a literary technique in which the writer is bound by some condition that imposes a pattern on how you write. I'll give several examples of these, but one of the most famous examples is illustrated here with 2 poems by a Japanese poet named Matsuo Basho. An old silent pond. A frog jumps into the pond. Splash. Silence again. And in the twilight rain, these brilliant hued hibiscus. A lovely sunset. These are poems, they date from about 1640, and these are examples of haiku. Haiku is sort of one of the most famous types of constrained writing. The haiku is a Japanese poem. It's a traditional style of poetry that has 3 lines in a 5-7-5 syllable pattern. So that's the constraint, is that you have to express your thoughts in 3 lines with 5 syllables, then 7 syllables, then 5 syllables, at least in the traditional Western understanding of a haiku. From a thematic point of view, haikus use short phrases and images of nature to evoke strong feelings and strong images. So I have 2 other haiku that I like. With everything I touch, everything I touch, with great tenderness, alas, pricks like a bramble, which is from the Japanese poet Kobayashi Issa, who lived around 1700s, and chittering monkey, in the spring he climbs treetops and thinks himself tall, by Makmu Ling, who is headmistress in the finishing school of Ba Sing Se, for those of you who are Avatar folks. But the idea of using numerical constraints on the number of syllabi or syllables that you use, actually lends itself to a pi-inspired variant of the haiku called the paiku. A paiku is a 3-line poem that uses a 3.14 syllable pattern. Like a haiku, paikus express Zen-like musings on math and science and the limit of our knowledge by using these very compact phrases. And so I'm just going to give you several examples of paiku written by me. I like pie, but just the fruit kind. What is pi? 3? I suck at math. Ratio, round, inside, outside. Eureka, thought Archimedes. This 2-stanza haiku will actually come back and be important to us later on in the talk. Young Newton, bonk, what a story. Triangle, sides, Pythagoras. One written by my daughter. My dog growls, bark, grumpy old hound. Nerd or geek? Me, best of both worlds. So haikus are actually a relatively young version of constrained writing inspired by pi. And there's kind of an older version that dates back to about the mid 1800s. To talk about it, I at least want to maybe talk about some other forms of constrained writing where the constraint is not on the syllables, but on the letters being used. So one type of constrained writing that you might have heard about is an acrostic. Acrostics are forms of writing in which the first letter of each word or sentence or verse forms a secondary message. If any of you have ever read Through the Looking Glass, the very, very end of that book after the story is over, it ends with a poem which is traditionally known as A Boat Beneath the Sunny Sky, in which Lewis Carroll talks about the loss of wonder in the 3 kids that he would tell his stories to, the 3 little girls, as they were growing up and becoming less inspired by Wonderland, and the hope that new children would become inspired by it. It's a lovely poem. A boat beneath a sunny sky, lingering onward dreamily in an evening of July. Children 3 that nestle near, eager eye and willing ear, pleased a simple tale to hear. Long has paled that sunny sky, echoes fade and memories die. Autumn frosts have slain July. Still she haunts me phantom-wise, Alice moving under skies never seen by waking eyes. Children yet the tale to hear, eager eye and willing ear, lovingly shall nestle near. In wonderland they lie, dreaming as the days go by, dreaming as the summers die. Ever drifting down the stream, lingering in a golden gleam. Life, what is it but a dream? This is a famous example of acrostic. If you focus only on the first letter of each line and read them in order, it spells out Alice Pleasance Little, who was one of the children three in the poem. Alice is in fact the model of the protagonist from Alice in Wonderland and Through the Looking Glass, a friend of Lewis Carroll. This is actually a picture taken of her by Lewis Carroll himself. It's a neat way to honor somebody. Another example of constrained writing is an abecedary. That's when the first letter of each word or sentence or verse is written in alphabetical order. A lot of little kid books, when you're trying to teach your kids the alphabet, take the form of abecedaries. A is for apple, B is for banana, C is for cucumber. One of my favorites is the Gashly Crumb Tinies by Edward Gorey, which is kind of a grim abecedary if you've never read it before. A is for Amy, who fell down the stairs. B is for Basil, assaulted by bears. C is for Clara, who wasted away. And D is for Desmond, thrown out of a sleigh. If that's not quite your vibe, several of the Psalms in the Bible are also abecedaries. If you read them, the first line of each verse is the alphabet in order. One of the most famous is Psalm 119, which I've got written here. Happy are they who are upright in the way, who walk in the law of the Lord. Happy are they who keep his testimonies, that seek him with whole heart. Yea, they do no unrighteousness, they walk in his ways. Thou hast ordained thy precepts, that we should observe them diligently. And I'll stop right here, because if you are paying attention, the first letters of each of these things are H, H, Y, and T, which are not the alphabet in order. But the Psalms weren't written in English. The Psalms were written in Hebrew. And if you translate them back into their original writing, then the first line of each sentence are the Hebrew alphabet in alphabetical order. A number of the Psalms fit this same pattern in their original tongue. Another type of constrained writing is a catarism, which is a poem in which the successive word length is increased each time. Maybe they go up by one, maybe they go up by two. One of my favorites is something called Doctor's Note by a linguistic artist named Pietry. Doctor's Note: I do not know where family doctors acquired illegibly perplexing handwriting. Nevertheless, extraordinary pharmaceutical intellectuality, counterbalancing indecipherability, transcendentalizes intercommunication's incomprehensibleness. If you were to take this poem and write it in a fixed font, a fixed length font, and take out the punctuation, each line increases by one each time. So these are just other forms of constrained writing where you can feel the numerical idea of the constraint, the idea of the first of something, of the first in an order, of the length of the words being important. And so that's going to bring me to the type of most famous pi-inspired writing constraint, which is the cadic. So in a cadic, the lengths of the words are the digits of pi in sequence. So the first word would have 3, the second word would have 1, the third word would have 4. So let me give you some examples of cadaics. So here's one from Joseph Schiffley from the 1960s. But a time I spent wandering in gloomy night, yon tower twinkling chimewise, loftily opportune. Out, up, and together came sudden to Sunday right, the one solemnly off to correct plenilune. If you were to take this poem and count the number of letters in each one of the words, but a time I spent wandering in gloomy night, yon tower tinkling chimewise, loftily opportune. Oops, I went too fast on that one. Out, up, and together came sudden to Sunday right, the one solemnly off to correct plenilune. Then what you find is a very long 30 decimal place approximation of the number pi. These cadaics are actually kind of clever because one of the constraints of a cadaic is you have to use the digits of pi, and sometimes the digits of pi include 0. And so how poets and authors have worked around that constraint has been very clever. One common one is illustrated in this poem by Gazis and Herman. All I know I could disregard is hardly worth our while relating. Thousands labored computing for pi, but obtained very little. In modern days, one can increase the pi figures utilizing built-up electric monsters. What a marvelous science, which is pi to 49 decimal places. And there is a 0 right here. And so how Geises and Herman get by that is in these stories, you have to have periods that end sentences, but any punctuation who appears before the end, like this dash in the word built up, functions as a 0. So one of the ways to write cadets is that all punctuation in the middle of a sentence counts as the 0. As another example of this, this is the first 2 paragraphs from a short story called To Explore a Memorial to Martians by another linguistic artist named Mike Keith from 1975. For a time, I tried exploring the gloomy shade. The thick darkness descended quickly. Tenseness lay in the twilight. Many groups of lights made the sky brighter and of lucidly patterned stars. My interest overcame fear. I carefully entered a nearby structure. The building signified the Martian dream. I, while dreading it, proceeded forward with slackened rate. Mars night continued to wax, growing peaceful. I slowed then calmly. So in this longer passage, which is seen up here as the digits of pi, there are multiple zeros who pop up. And in the passage, any piece of punctuation who appears before the final period act as the zeros. So this is one of the ways in which to write pi, or to write cadets, where you're bound by the digits of pi. It turns out that's not the only way. There is a slightly different attack, and to show you that slightly different attack, I will bring back that almost raven poem that we had at the very, very beginning. The poem, including the title Poe Near a Raven, is a fairly long cadaic that gives us digits of pi. And because the author in this case is trying to emulate the style of Poe, he's going to need to have lots of punctuation, commas and dashes and quotation marks inside the text itself. And so Keith's solution to the how do you get a 0 in here is he uses 10-letter words. So anytime you see a word that has 10 letters in it, that stands for the zeros in the decimal expansion of pi. And then you're allowed to use any kind of punctuation whatsoever. So I've already read this at the beginning. I won't read the poem one more time, although I will point out for those of you who know The Raven is actually an 18 stanza poem. And Mike Heath didn't stop with the first 2. He actually wrote an 18 stanza variation on the Raven, and it spells out the first 740 digits of pi, including the final observations, original EPO redone by measuring circles. In fact, Mike Keith is sort of the world champion when it comes to creating cadaics. He's actually taken that poem and extended it to be the first chapter in a short story called the Cadaic Cadenza. It's written entirely in what's called standard Pilish nowadays. And standard Pilish is the art of writing cadaics in which the punctuation is irrelevant. Numbers that anytime a 0 would pop up, you would use a 10-letter word. And anytime you use a word with more than 10 letters in it, like 11, 12, or 13 characters, that just means a 1, 2, 1, 3 as it pops up in pi. So there's sort of a standardized way of writing these stories. The Cadaic Cadenza is an interesting work because it tells the story of a person who wakes up one morning to find that all of the books in his library have slightly changed. They're not the way he quite remembers them. And as the story goes on, he reads a section, then ponders, reads another book, ponders. He realizes that all of his works, and in fact his very life, is being rewritten by the digits of pi. As a work of fiction itself, the Cadaic Cadenza spells out the first 3,835 digits of pi, and it has versions of Jabberwocky, T.S. Eliot's The Love Song of Geoffrey Prufrock, Hamlet's Yorick Soliloquy, and Carl Sandburg's Grass, rendered as part of a longer Cadaic. So it's a pretty impressive piece of art. It is, believe it or not, not the longest Cadaic out there. In 2010, Mike Keith went and published the first novel that's written entirely in standard Polish, the first Cadaic length novel called Not Awake, which of course the Cadaic itself. And it has the first 10,000 digits of pi spread out across 10 chapters. It's an interesting read. It has short stories in it. There's a small play as part of the novel. You can fetch it from Amazon on Kindle for $3.14. Now, one of the things that people sometimes ask at this point is, why? Why would you go and make a 10,000 word decimal approximation of pi and somehow translate that into a story? And so this is just me making a tiny shout out to constrained artwork in general, and also making a tiny plug for stuff of art that I still get to go and do. Every morning when my kids get ready for school, they draw a squiggle on a napkin, and I take that squiggle and turn it into a picture, which is then put into their lunchbox, and then they can see what they got at lunchtime. And so here are 6 different squiggles that my kids or my wife have given me. And it's sort of a neat artistic challenge to go and take that shape and to expand on the constraints you're given and turn that into something novel and unexpected and different. I lack the skills to be able to do it fairly well as a poet, but I can do it pretty well with Sharpie on a napkin. And so I just wanted to kind of give a plug for the idea of constrained artwork as a thing. Now, in order to make Cadaics, you have to know the decimal expansion of pi. And so that's going to move me into part 2, where we need to talk a little bit about the math of these things. If you were interested in creating a Cadaic from the ground up, could you find the decimal approximation of pi yourself and then turn that into a poem? And so let's talk about how we would go and find the digits of pi. Where does the 3.14159 come from? So we've seen that where there are circles, there's pi in art. So how do the digits of pi come from circles? Well, given a circle, there are 2 really simple things that we could measure on it. We could measure the diameter, kind of how far across the circle goes, and we could measure the circumference. How long around does it take to wrap the circle? One of those is clearly longer than the other, right? The circumference is longer than the diameter. And so pi is simply the ratio of the longer side to the shorter side. How much longer is the circumference than the diameter? So in formulas, we write it as a fraction. Pi is equal to the circumference divided by the diameter. And that one formula is how we're going to go and pull all of the digits of pi out. So to see how you could get all of those numbers from this one fact, let's just do a thought experiment together here. So a thought experiment, imagine putting your mind's eye a circular field, and imagine a diameter, so walking across that circular field. Now, if instead of walking across the circular field, you walked along the periphery of that, then it would be clear that the red distance in my picture, the walk around the outside edge of the circle, would be a longer distance than walking straight across, right? Shortest distance between 2 points is a straight line. That red distance is definitely longer. And that statement would be true twice, on the way forward and on the way back. So pictorially, we've just argued that one circumference, one full trip around the circle, is greater than 2 diameters, the trip back and forth. On the other hand, if you were to go and take those 2 diameters, expand them into 4 and wrap them around the circle, it's clear that the perimeter of the square bounding the circle, the walk around the square field enclosing the circle, would be greater than the circumference itself. And so the circumference would be less than 4 diameters, the 4 sides wrapped around the square. So that means, as just a thought experiment, we're able to show that on any circle in the universe, twice the diameter is smaller than the circumference, which itself is smaller than 4 times the diameter. Now, if we were to write this as a fraction over to the denominator d, that would say 2 is less than the ratio of c to d, which is less than 4. And the ratio of c to d, how much longer the circumference is than the diameter, that was just our number pi. And so as just a simple thought exercise, we can conclude that whatever the number pi is, it's always between 2 and 4. And so if you're going to take just a quick rough estimate, pi is about 3, which is the first digit in pi's decimal expansion. It's also one of the world's oldest estimates of the number pi. This value for the ratio of circumference to diameter shows up in a number of different cultures and historical artifacts through history. It's literally as old as dirt. In fact, here's an example. This is a clay tablet that was taken from Mesopotamia around 700 BCE. In Mesopotamia, they didn't have papyrus or paper style writing. They would take the clay and the silt from the Tigris and Euphrates. They would pat it down into something relatively flat and then use reeds to carve letter forms into, using a Babylonian alphabet called cuneiform. When these clay tablets were left in the sun over the course of a day, they would harden into these rock carvings that you see right here. We've got hundreds and thousands of these things in museums across the world. The very first superhero story, if you'd like, the Epic of Gilgamesh, is recorded as a clay tablet written in cuneiform. This particular clay tablet that I'm showing right here is one of the earliest references to the periphery of a circle being thrice the diameter of the circle. And you can kind of see that there's a circle carved into the shape. The cuneiform asks for how to compute the circumference of such an object. And attached to the outside of that circumference, there is the number 3 written in cuneiform, with the remaining calculations showing that you would multiply by 3. This approximation also pops up in literary sources. If, for example, you were to go and crack open your copy of the Holy Bible or the Quran or the Torah, pull yourself open to 1 King, chapter 7, verse 23. This is a description of the Temple of Solomon. In it, it says that he, King Solomon, made a sea of cast metal, circular in compass, measuring 10 cubits from rim to rim, 5 cubits high, and it took a line of 30 cubits to measure around it. So if I focus on just 2 aspects of that it took 10 cubits to measure from rim to rim, and that it took 30 cubits to measure around it, you're seeing once again circumference, diameter, get that right. The circumference is roughly 3 times the diameter. This is sometimes known as the biblical approximation of pi. But that's just one decimal place. We've seen cadaics that go to thousands and thousands of decimal places in that writing style. So how do you get that kind of level of precision? Well, with just a little bit of geometry and a heck of a lot of patience. And so I want to go through 2 historical examples to kind of show you what the idea is and give you sort of a quick remixed version of history. So the first place we're going to go to is ancient Greece, and we're going to take a look at Archimedes. The Greek Archimedes of Syracuse, who lived around 300 BCE, was a world famous mathematician, physicist, inventor, occasional streaker. He was also the first guy to rigorously investigate the peripheral constant, what we nowadays call pi, the letter pi being the first letter in peripheral constant. And he used a method called the method of exhaustion, which centered on 3 big ideas. And so let's take a look at what these 3 ideas were, because they're going to govern how almost every culture would look at pi for a millennium and a half. Idea number 1 was that if you were to enclose a circle between 2 of the exact same polygon, then the circumference of the circle would be bounded by those 2 perimeters. Since it was easy to work out the perimeters of objects with straight sides, you would have bounds for estimating the length of this curved object. So if, for example, you had a circle of diameter exactly 1, then its circumference would be exactly pi, because that's what pi is, how much longer the circumference is than the diameter. So imagine that you were to put that circle of radius 1 inside a square, that's the red shape, and stick a square inside of it. If you were to go and use some of your high school geometry, you could figure out that the exterior square has sides of length 1, since they're all diameters. The interior square has sides of length 1 over root 2 by the Pythagorean theorem. And so the exterior perimeter would be 4. The interior perimeter would be 4 1 over root 2s, which is about 2.8. And the circumference would have to be in between those 2 values. And so this gives us a better approximation that pi has to live between 2.8 and 4. So that was a better approximation than just our thought experiment of 2 and 4. That was idea number 1, enclose a circle between 2 shapes. Idea number 2, the more sides you use on that polygon, the better these bounds are going to be. So instead of enclosing a circle in a 4-sided shape, enclose it in a 6-sided one. Hexagons all around. So if we were to go back and say we had that diameter of radius 1, we could do a bunch of geometry and find that the interior hexagon would have side lengths of 1/2, And the exterior hexagon would have side lengths of 1 over root 3. So those are side lengths of 0.5 and 0.57 respectively. If we were to go and count up the 6 sides there, we would find that the interior perimeter is exactly 3, and the exterior perimeter is just shy of 3.5. And so we would conclude that the circumference of the circle, pi, has to be wedged in between these two perimeters. Pi has to be between 3 and 3.5. So we've managed to the gap that pi is allowed to play in has gotten a little bit smaller. So what would be the third idea? Well, the more sides you have on the polygon, the more these interior and exterior perimeters match. And so this animation right here is just sort of showing you what happens as I add a side over and over and over again. When you get to about 12 or 13 sides, you don't really even see a blue and a red curve anymore. You just sort of see what looks like a purple polygon. And by the time you get to 24 sides, it doesn't even look like a polygon, it looks like a circle. And so Archimedes' third idea was, rather than just randomly pick sides, he came up with a method for doubling the number of sides. So if he knew what the perimeters were for a polygon of a specific size, he was able to find a formula that told him what the side lengths would be if the polygon had twice as many sides. So if you knew what the side lengths were on a 6-sided polygon, and we did that earlier, you could compute by a formula rather than geometry the side lengths on the 12-sided shape. And then you could double again and find the side lengths on a 24-sided shape. We're not going to go and do all of that math there. This is not a hardcore math talk, but if you want the formula, it's down there. I'll just show you that what Archimedes did is he started with a 6-sided object and then doubled to 12, to 24, to 48, going up to 96. And so he used a 96-sided polygon on the inside and the outside. And here's the summary of his work. When he got to 96 sides, both the inner side length and the outer side length differed by less than 1/100,000th, which he didn't really have the mathematical symbols to continue with any further. And so the inner perimeter is approximately 3.141. The outer perimeter is approximately 3.143. And so if we split the difference between those two numbers, we could conclude that pi is approximately 3.142, and we would be accurate to within 1/1000th of the correct value, which is a pretty good approximation. It turns out that this is also really close to 3 1/7. 0.142 is darn near 1/7. And so the fraction 3 1/7 is sometimes called the Archimedean approximation. As an improper fraction, it's 22/7. And in England, where they write the days before the months, 22/7 is July 22nd, which is the British version of Pi Day. Now, the second stop in my little quick history tour is to go to China and take a look at the Chinese mathematician Zhu Shangji, who took Archimedes' work a step further with 2 more insights. So first, he figured out how to go and relate the area of a circle to the diameter rather than circumference to diameter by the formula pi is area of a circle is 1/4 pi times the diameter squared. If you've never seen any kind of argument for an area formula for a circle, they all follow this basic idea, which was first articulated by these Chinese mathematicians. And it's a great argument. Basically, the idea goes and says, take your circle and chop it up like you would any kind of pizza. More slices, the better. Then take half of those pizza slices and arrange them on one side of the table, half of the pizza slices on the other side of the table, and then slide them together to form this big, long caterpillar shape. Now, if you kind of squint your eyes a little bit, that's kind of shaped like a parallelogram. And if you were to slice the excess of one pizza off and stick it on the other end, you're talking a rectangle. So take any of the pieces, slice them up, and re-put them together, you have what's almost a rectangle. How long is the rectangle? Well, it's made out of the crusts of half of the pieces of pizza, so it's the length of half the circle, so half the circumference. How tall is this rectangle? Well, it's the length of any one of those pizzas, which was a radius, which is half a diameter. And so you multiply those two things together, length times width, and you get the area of the rectangle shown here is the product of half a circumference and half a diameter, or 1/4 of the product of the circumference and diameter. And so since that's approximately the area of a circle, we'd say that the area is 1/2 the circumference times 1/2 the diameter, or a quarter of their product. But circumference is pi times the diameter. And so that gets us 1/4 pi d squared. So the more pieces you slice, the more this looks like an approximation. That's a very Archimedean idea. So I just wanted to show you some pictures just to kind of convince you that if you didn't think the weird caterpillar before looked very rectangular, imagine slicing it into 100 pieces, and the shape you're going to get is very much a rectangle. So that's idea number one. You could go and use areas rather than circumferences to calculate pi. Idea number two was that using areas made these calculations easier. So rather than using perimeters to bound pi, you could use areas to bound pi. And it was easier to do these area calculations. And so what Zhu Shangji did was he repeated Archimedes' method, but instead of measuring the perimeters, he measured the areas of the inside and the outside polygons. And so here's a collection of him repeating Archimedes' work. And if you look at the final values at 96 polygons, the number on the left is approximately 3.14, and the number on the right is approximately 3.14 to the nearest 100th. But Zhu went farther than that. He doubled over and over and over again, eventually computing areas for polygons that had almost 13,000 sides on them. In those approximations, he found that the inner and the outer areas differed only in that 7th decimal place. And so we could conclude that if we average the two of them together, pi is approximately 3.141596, and the error of that approximation is less than 1/100,000,000th. It turns out that this is also very close to the fraction 355 113ths. And so this fraction is sometimes called the Chinese approximation. When I was a TA, and I had students who were Chinese nationals who would come to the United States to study, they would very often use 22/7 and 355 113ths as fast calculator exercises for computing pi when it showed up in equations. So these are just approximations, though. Using methods that weren't available to the ancients, that were available starting in the later 1700s, we could use calculus to find exact formulas for pi. And once you have an exact formula for pi, you don't have to approximate anything anymore. You just keep adding more and more terms to it. So I can't show you these without having a whole bunch of calculus, but I would at least like to show you what they look like. So for example, we saw that 3 1/7 was a good approximation of pi. So 3 1/6 written here is not a great one, but it becomes better if I replace that 6 with 6 plus 3 times 3 over 6. This is a better approximation of pi, but it's still an approximation. But it becomes a better approximation if I replace that last 6 with a 6 plus 5 over 5 over 6. And this becomes a better approximation if I replace that last 6 with a 6 plus 7 times 7 over 6. This pattern isn't just these 4 terms. If you were to repeat this pattern on over and over and over again, always replacing that final 6 with the next odd 6 plus the next odd number times that odd number over 6, the resulting expression is exactly pi. There are hundreds of these kinds of formulas who express pi as these beautiful geometric constructs, but they're also just aesthetically pleasing. I mean, look at this equation. Even if you didn't know that it was pi exactly, its structure has nice artistic balance to it. In fact, the very first formula for pi that was exact comes from one of those Sanskrit poems that we talked about earlier. The poem reads, "For that which part the circle takes of the square, the first term is unity. The succeeding terms are iteratively divided by odd quantities, and then the part is found by adding the terms of odd rank while subtracting those of even rank." Clearly, it loses something in the translation to English. But what it says is it says this: if you've got a square and you stick a circle inside of it, the part at which the circle takes up, how much of the circle how much of the square does the circle take up? That's exactly pi over 4, because that was our area formula. So that's the first first line. For that which part the circle takes of the square, in other words, pi over 4. The first term is unity, so pi over 4 is equal to 1. But there are succeeding terms that you get by dividing by the odd quantities. So 1 divided by 3, 1 divided by 5, 1 divided by 7, 1 divided by 9. That's the third line. The fourth and fifth lines together say you add the terms of odd rank while subtracting the terms of even. So you add 1, 1/5, 1/9, 1/13. You subtract 1/3, 1/7, 1/11, 1/15. And the resulting expression 1 minus a third plus a fifth minus a seventh plus a ninth minus 11th, continued on forever, becomes pi over 4. So with either of these two formulas, this is actually a pretty slow converging formula. That previous cascading fraction gets you very accurate results very, very quickly. And so now we've gone to the ability to build pi from the ground up. So suppose you were interested in making a pi, you're interested in using pi. We're going to bring the whole talk full circle in the last few minutes and use poems to remember the digits of pi. So this is a common genre of cadets, the pi mnemonics. And so they use the structure of pi, Pi-lish poems to help you remember the digits of pi. And I love this, the symmetry of this, where the digits of pi are used to create the poems, and then the poems are designed to tell you the digits of pi. So I'm going to close with just sort of a couple of famous examples of these. One of these is by Dmitri Borgman, the guy who wrote the long cascading poem from earlier. May I draw a circle? Is a mnemonic that gets you up to for decimal precision for pi. A slightly longer one is Now I Need a Verse Recalling Pi by Fisher and Hayden from 1965, which apparently was a banner year for making cadets. A slightly longer poem, Now I Wish I Could Recollect Pi. Eureka, cried the great inventor. Christmas pudding, Christmas pie is the problem's very center, which gets you a 20, about a 30 decimal place approximation of pi. A slightly longer poem, See, I Need a Rhyme Assisting My Feeble Brain, Its Tasks Sometime Resisting. Efforts laborious can by its witchery grow easier, so hidden here are the decimals of the circle's periphery. A poem from 1914 in a primer. A slightly longer one, gets one extra digit, is May I Have a Month, Professor, to figure these, you brain assessor. Calculate, student, calculate now. As the figuring gets longer, my friend, hope you get stronger, and no figures incorrect allow, by Buckman from 1953. The first two lines of this, May I Have a Month, Professor, to figure these, you brain assessor, are one of my favorite ways to remember pi. There's actually a number of these things in foreign languages too. Here is a French mnemonic. Que j'aime à faire prendre un nombre utile aux sages, glorieux alchimie d'artiste ingénieux, trois de qui s'accuse à mon corps la mémoire. Here's one in German, which I don't speak, and one in Polish, which I'm not even sure how you pronounce words that have no vowels in them, and I'm Polish. But in their English translations, these are different stories of how to remember pi. How I love to teach a number useful to wise men, glorious Archimedes, ingenious artist, you of whom Syracuse still loves the memory. The German poem, oh, how this pi gives so many people such trouble. Learn them all, young men, the easy verses, so that, for instance, this is easy to keep in mind. My favorite is this Polish one because it tells you exactly what a cadet does. To make from a few lines for the use of science, to create by words and write exactly, not by eye, the number pi. Count how many letters are in each word, thus you should remember. So a whole bunch of pi mnemonics for you thrown at you really quickly. Every time I've ever done this for other people, I can kind of, when I'm in a room, I can kind of see the common expression on all their faces. God, I need a drink. Alcoholic, of course. After all these lectures involving cadaic mnemonics for pi. So one last cadaic for you. So wrapping things up, the number pi is this ubiquitous part of the human experience, whether it's a mathematical or artistic part, whether it be the discovering of its digits for the first time, or writing poetry that's bound by these digits for the umpteenth time, thinking about pi is this profoundly human experience. And so I would like to close with one last haiku. In the end, pi is knowable. So thank you, everybody, for listening to me. In case you're interested, you can reach me by email at traviskowalski@stsnt.edu. If you're interested in the squiggle napkins that I showed you, I'm on Instagram at squiggle.napkin.travis. And Mike Heath, the Pi-lish author who wrote the Near a Raven poem at the very, very beginning, you can read a lot of his work at his website at www.cadaic.net. So once again, thank you very much. And I will stop the share and turn the time over for questions from anybody.
Thank you. That was very informative. I didn't know there was that much into pi. So besides the equation itself. There was a question. If anyone has any questions, by the way, please feel free to put them in the chat or the Q&A. I'll watch for them. You did have a request asking, would you consider doing another presentation on fractional fractal art.
It's on
I'm probably-
fractal art.
Fractal art. Yeah, I'm probably
another-
reading that wrong. I'm sorry.
Yeah, that's another fun one to do. I've done projects with students building fractal art before. So yes, I would be happy to go and do something like that. Those ones are beautiful things as well.
I always enjoy seeing your napkin art. And I think people forget that that's one of your hidden talents that not many people know about, but it's really beautiful. You did a really good job. So as we're finishing up the rest of the hour, again, if you have any questions, please feel free to drop them in. As always, we're looking for feedback on our events, or if there's a topic that you would like us to feature, I'm going to drop the survey in the chat, so please feel free to fill that out. One thing I did not get to as we're waiting, this Friday, for those of you who are in the Denver area, tomorrow night at 6 o'clock, we are doing an alumni event. Excited to be in person. It is a heavy appetizer event, and then there is a cash bar. So we'd love to have you. I will drop the information in the chat also, so you can click on that and see. That'll give you the address to where the event is. It's in the Cherry Creek area. So we'd be happy to help you. You had some really good rave reviews. So good job. Thank you. Thank you so much.
Thank you again.
Oh, wondering if you can share the recording with me today. It's my friend's birthday. P. Talum, yes, I can get you the recording today. So after we're done, we'll get it uploaded. So